If a silicon diffusion is doped with borons, these are acceptors. This is important, we'll come back to it in a second. At a concentration of 1.4 times 1015 cubic meters, this is just a value that we have. What is the resistivity of this diffusion in ohms per centimeters? So we're going to assume Ni, we have a micro N and then a micro P. This is an acceptor, and if it's an acceptor, that means that what we have right here is going to be P right here, and this will be very explanatory, whatever, when we look in the notes that aren't mine, but they're professors in the description below the like button. On page approximately 28, 29, we have some examples there, and there are some equations. The first equation that we are going to use is the following. We are going to want to look at the mass action law, and we're going to look at hole concentration, but we're going to look at the electron density for this one because we're looking for NP. And this is going to be equal to, we have our Ni squared divided by our PP. So with this, we can put the Ni squared, we're just going to plug it in, 1.45 times 10 raised to the power of 10. This is going to be squared, and then we have our centimeters raised to the -6. Just because of the square and the centimeters on the bottom, we're just putting it on the top here. Then we have our PP, of course, and that's going to be 1.4 times 10 to the 15 cubic meters cubed. So now we're just going to plug this into a calculator, and once we do that, we're going to have an NP be equal to a 150,178.5714 cubic meters -3. Then we can just omit or just put the units over here for now. So that's going to be our NP. Now we're not done yet because that's not how we calculate resistivity. We're going to move on to our next step, and for resistivity, we're actually going to be looking at the semiconductor conductivity. And then we're going to put 1 over this, and that's how we would get that. So for semiconductor conductivity, we're going to use a constant out front. It's electronic charge. This is if we are accepting or donating, and this is equal to 1.6 times 10 to the -19. We have some units here, but just for simplicity, I'm going to omit units for the rest of this until we get to the end. It is important to know the units though, so just know the units here, and then when we plug everything in, the units should kind of even out together to get what we would have here in the end. And now we're going to plug everything in based on the formula. So again, omitting units, we have this 400, and we're going to take this 400 and we're going to multiply it by, because it's our micro P, our P. And what is the P? Well, the P is what we were given right here. And I'll actually do this in a different color right now. So this P is going to be our 1.4 times 10 raised to the power of 15. Now let's go back to blue, and with back to blue, we are going to plug in our micro N, which is just 1,000. We are going to have our N, because remember, this is our micro P, this is our micro N, so this is P. This should be multiplying it by N. And well, N is going to be this value right here. So we're multiplying it by N, so we can just put NP like this, and then we can close this off. So after we plug all of this into a calculator, we're going to get that this is approximately equal to 0.896, and I believe that's a sigma. So our sigma is equal to this. And now we're going to want to find the equivalent to resistivity. I forget exactly what the symbol is, but this is for resistivity, and it's equal to 1 over the sigma, which is just going to be 1 over 0.896. And that's going to give us approximately 11.1607. And that, again, if we had the units, would be ohms per centimeters. So when we plug this in, it's going to be 11.1607 for this problem. Numbers are different. You would just rearrange the numbers and use the same equation. That's going to be it for this problem. And more can be found just like it in the playlist link below the like button for anything in this section.